Okay, so what I want to talk about is a collaboration first with Jonathan Bowden, Sebastian Hensel. Jonathan is here, yes. Sebastian Hensel, Kathryn Mann, and Richard Webb, but this is for the case of the two torus. And a work with Pierre-Antoine Guihéneuf where we focus on the case of homogeneous surfaces. As the case of the two torus is a bit different, I will focus on, in this talk, on the case of homogeneous surface, but the techniques we used with Pierre-Antoine are similar to the techniques we used in the case of the two torus. Okay, so in the whole talk I will fix S an orientable closed surface, and I suppose it has a genus greater than or equal to 2, but all the results can extend to the case of the torus with some little modifications. And as I'm a dynamicist, the group I'm interested in is a group of homeomorphisms of S, and more specially a normal subgroup of it, which is just the connected component of the identity in this group. Okay, let's call it just S. Okay, and what I'm going to talk about is about some geometric object, which is called the fine curve graph, which is a Gromov-hyperbolic metric space on which this big group acts by isometries. And so the goal of this talk is to show you, to give you a little glimpse of the dictionary that exists between the isometric action of this group on this geometric object and the actual dynamics of elements of this group on the surface. Okay, so first of all, I have to define what this fine curve graph is. Okay, it works like that. So, okay, let's start with defining the fine curve graph, but before defining this new object, I want to go back to the more classical object, which is called just the curve graph, which was defined by Harvey, so classical setting. So this is what we call the curve graph of S. We usually denote it by C of S. So it's already kind of a big graph because it's a graph whose vertices are isotopy classes of essential simple closed curves. So isotopy classes, okay, I should say Harvey, of simple closed curves, essential simple closed curves. Here, essential just means that you don't bound a disk. You're not trivially you don't represent the trivial homotopy class. And you put an edge between two vertices if those two isotopy classes have representatives which are disjoint. If there exist disjoint representatives in this isotopy class. Okay, so why do we care about this graph? Okay, first I want to make it into a metric space. To make it into a metric space, I set that each edge has a length 1, and it turns it into a metric space. So why do we care about this object? It's because on this object you have an action of the group of homeomorphisms of S by isometries. So it gives you another way to see this group. Okay, but of course, why does it act is just because if you have disjoint curves, they are sent by such a homeomorphism into disjoint curves, so length is preserved. But the action is not faithful. So, of course, if your homeomorphism is isotopic to the identity, it will act trivially. So if we want a faithful action, we have to look at the mapping class group. And okay, as the group I'm very interested in is this one. We kind of have a problem, but still it's a nice tool to study the mapping class group. So this group. An important property from the geometric group theory viewpoint is that this curve graph, so this is a theorem by Major and Minsky. I think in 1998. This graph is a Gromov-hyperbolic space. Okay, I will not define what a Gromov-hyperbolic space is, but it's roughly it's a space which has similar properties to the hyperbolic plane, let's say. We won't need the definition, but this kind of space plays an important role in geometric group theory. So, okay, and the last thing I wanted to say is that here I took a closed surface, but if you look at punctured surface, you can also define such curve graph with the same properties. So you can define the curve graph of a punctured surface. We will need it in this talk. Okay, so that was a classical setting. Now I will start from this classical setting and explain you how we define this fine curve graph. And I will use a different color for this, maybe red. Okay, so now I want to define the, this is not the classical setting, I want to define the fine curve graph. So the fine curve graph of S was defined by Jonathan Bowden, Sebastian Hensel, and Richard Webb. It's the same at the beginning. In a sense, it's a graph which is easier to define, but it will be much bigger than the curve graph of S because we don't take isotopic classes of essential simple closed curve. We just take as vertices any essential simple closed curve. And you put an edge between two vertices if they are just disjoint. So of course it gives you a very big graph because the valence of each vertex is uncountable. But still, first we have an interesting property, which is that the whole group of homeomorphism of the surface, and in particular those isotopic to the identity, this whole group acts faithfully on, okay, the fine curve graph is C dagger is denoting like that, C dagger of S, by isometries for the same reasons. And Jonathan Bowden, Sebastian Hensel, and Richard Webb were able to prove
excuse me, are the curves parametrized?
The curves, no. You don't, no. You just look at like subsets. They proved that this fine curve graph is Gromov-hyperbolic. And they use this graph. I think it was mentioned in the talk by Vincent Humilière. They use this graph to prove that the commutator length on the group of homeomorphism isotopic to the identity of S is unbounded. Okay, so from a Gromov-hyperbolic space, you have ways to construct quasimorphisms, and with this Gromov-hyperbolic space, they were able to build those quasimorphisms. Okay. Last thing before I move on. Okay, so I want to say something about isometries of a metric space. So if I have a metric space, the property I will look at is a property to act hyperbolically on this metric space. What does it mean? So take an isometry. We say that this isometry is hyperbolic if there exists a point in your space, or equivalently for all points in your space. Okay, I will explain a little more. Such that you go to infinity at linear speed, at least linear speed. Okay, some comments. First, this limit always exists by Feket's lemma because this quantity is sublinear as f is an isometry. And moreover, as f is an isometry, still this limit does not depend on the chosen x. So here is the same as saying that it's true for any y. Okay. So now our question, the question we will be interested in this talk is to describe what is the dynamics of homeomorphisms of S for which their isometric action on this fine curve graph is hyperbolic. So I will just write roughly which f act hyperbolically on S. Okay, so it's a small part of this dictionary we want to set up, but that's the question I'm interested in this talk. And at the end, I will give a complete answer. Okay. So to describe it dynamically, I need some dynamical notions. So now I will need two dynamical notions, in fact. But I will first speak about pseudo-Anosov homeomorphisms. I suppose a lot of you know what it is, but maybe not all of you, so I will give a quick definition of what a pseudo-Anosov homeomorphism is. Okay, if you take a matrix in SL2 of R, I start with Anosov homeomorphisms with eigenvalues lambda real, say, okay, between 0 and 1, and lambda minus 1.
Sorry, do you want to act in which acts hyperbolical
on the fine curve graph? Thank you. Yes. On the fine curve graph. And I mean, this is where I have an action by isometries. Yes. Thank you. Okay. So, okay. In this case, your matrix acts, of course, on R2 and preserves the integer lattice, the Z2 integer lattice. So it quotients down to some homeomorphism of the two torus. SL2Z, thank you, yes. Okay, there are lots of mistakes. That's to make sure the audience is aware of what I'm doing. So there is a prize for the... Okay. So the eigenvalue of A gives you define two foliations on your two torus, and one of these foliations is contracted by the dynamics in the sense that if you take a segment on it, you iterate, it will get smaller and smaller and at exponential speed. And one is expanding. So one way to say it's expanding is that if you take a segment on this second foliation, you iterate backwards, you iterate by the inverse, it gets smaller and smaller with an exponential speed. So A has two transverse invariant foliations. One which is exponentially contracted. I will just put contracted. And the other one being exponentially expanded. But of course, if you move on to higher genus surfaces, you get a problem because on higher genus surfaces, for topological reasons, there is no foliation. So you're kind of forced to put some singularities to your foliation to define a similar notion. So now I take my surface S. Some f like that is called a pseudo-Anosov homeomorphism. Okay, so you have to allow singularity. So the singularity will be a finite set. And then, by removing this singularity, you will have actual foliations of S minus F. Okay, so I need two transverse foliations, as in the case of the torus, of S minus F, one which is contracted by F, two transverse invariant also, one which is contracted in the same sense as in the case of the torus, the other one being expanded. And to make a complete definition, you have to add some conditions on near the singularities. Well, you have some models of what it must look like close to singularities, which are like branched cover over some model. Okay, so why do we care about pseudo-Anosov homeomorphism? It's because you have a classification of isotopy classes of homeomorphism of S, which is called the Nielsen-Thurston classification. I will not state it, but I will state one corollary of it, which I will need in this talk, which is the following. If you take any F homeomorphism of S, okay, I forgot to say, you can also extend this notion to the case with mark points. Okay. If F satisfies the following property, namely that for any alpha essential simple closed curve, and for any n bigger than 1, Fn of alpha is not isotopic to alpha, then F is isotopic to a pseudo-Anosov homeomorphism. So this is a consequence of the Nielsen-Thurston classification. Okay, now that I've talked about pseudo-Anosov homeomorphisms, I can give you a first statement of the theorem. So the following are equivalent. So take the homeomorphism isotopic to the identity. TFAAE means the following are equivalent. First, F acts hyperbolically on the fine curve graph. And second, there exists a finite subset such that if you look at the isotopy class of the marked surface S minus F, this is isotopic to a pseudo-Anosov homeomorphism. So in this theorem, there is one implication which is easy to prove. I mean, easy given all the existing, already existing theorems. And another one which requires more work. So I will start with the easy implication. Yes.
Do you mean the capital F is invariant under?
Yes. Yes. Thank you. F invariant. Globally, yes. You can permute it. You have to think of it as a set of periodic points of F. Okay, so the easy implication is 2 implies 1. But it's easy because we use a theorem by Mazur-Minsky. Which says that any pseudo-Anosov mapping class acts hyperbolically on the fine curve graph. On the classical curve graph. Okay. In fact, for a lot of properties that we prove on the fine curve graph, we actually use properties from the classical curve graph to prove them. So the method I will talk about here is kind of something that we use a lot in this context. So the idea is that if you take some element which is just an actual curve, you suppose that it is disjoint from this set F. Okay. And I want to prove that the translation length is big. So how do I do that? I want to compute this quantity. See that it grows at linear speed. To do this, I will compare this quantity to some quantity on some classical curve graph. So I will look at the classical curve graph on S minus F. So we have such an inequality. This inequality is easy to prove. You just take some geodesic here a geodesic on the graph is just given by a sequence of vertices of the graph. So you take two consecutive vertices in this geodesic. Those are disjoint curves. Okay? So either these curves are different isotopy classes, and then there are distance 1 in this graph, or they are the same isotopy class, and in this case they are distance 0. So all you can do is contract distances. Of course, you have to make sure everyone in the geodesic avoid F, but you can do it by perturbing, and then you still have a geodesic. So I divide by n, but then Mazur-Minsky tells me that this tends to something strictly positive. So this is implied by Mazur-Minsky theorem, so that this tends to something strictly positive, and so this implies that f acts hyperbolically on the fine curve graph. Is this okay? Okay. The other implication, I don't know how to do it directly. And to do this other implication, I need to use another tool, namely something which I call which is called, sorry, not only me, the ergodic rotation set of homeomorphisms. So I'm going to talk about it. So it must be T2 maybe, yes. Ah, okay. We cannot move two blackboards at the same time. Okay, so what is this ergodic rotation set? So this is a quantity which is defined only for homeomorphism isotopic to the identity. So as it is isotopic to the identity, I can pick an isotopy between F and the identity. The idea is that, okay, this is something quite common in surface dynamics. You have to have the idea that this isotopy will kind of play the role of flow lines when you're looking at flows, when you're to study this dynamics. So I will extend this isotopy just by setting that for any t in R, I will say that ft is just ft minus the lower integer part of t composed with f composed t times. Okay, so this is what we call a rotation set. To say something about rotation, what we will do is that we will take a point, we will follow this kind of flow line for a long time, then we will close this thing to obtain a closed curve, and then we it's a homological rotation set, so we will take the homology class of this thing. And we want to see the asymptotic behavior of these objects. And this will give us somehow the way the orbit rotates in the homological sense when we iterate. So these are ideas back to Schwarzman. Okay, so pick a point x. Okay, for any point x, y also, I need something to close the orbit. So I did not like that a geodesic between. Okay, you don't really need a Riemannian structure really. You just need to pick segments of uniformly bounded lengths between any 2 points in your surface. Okay, so pick a point x in your surface, pick an integer n, and I will denote by cxn the homology class, so in H1, of the following path, which is the concatenation of ft of x during a time n with something which closes the orbit. So I close the orbit just by taking some short path between f to the n of x to x. And basically what we want to do is that we want to divide by n and take the limit. So the limit does not always exist. Sometimes you can have many accumulation points. But if you take an ergodic measure, we have a theorem that says that those quantities, when you divide them by n, will almost surely have limits. So I take, okay, I will explain what ergodic means briefly. An F ergodic measure, mu is an F ergodic measure on S. So what is an F ergodic measure? It means that if you have an invariant Borelian set, from the point of view of mu, F is really mixing up all the dynamics. So if you are invariant, you are either everything or nothing. So this implies that either you're nothing, from the point of view of mu is just that the measure is 0, or you're everything. Okay. So we have a proposition which is a consequence of the Birkhoff ergodic theorem. If you don't know what the Birkhoff ergodic theorem is, that's not a problem. You just take this proposition for granted. Right, okay, this is not the Birkhoff ergodic theorem. This is a consequence of so for mu, okay, something, okay, I will say it afterwards. For mu, almost every x in S, the sequence of homological vectors, so this is a sequence in H1 of S with real coefficients. Okay, there exists, I should have started like that, there exists some homological vector which I denote by R of mu, such that for mu almost any point in S, this sequence of homological vectors converges to R of mu.
Sorry, what's the first line? So mu is a Gaussian measure, but what was before that?
There exists some vector which depends only on mu. Such that if I take...
So you have fixed ergodic measure now, which is...
I have fixed an ergodic measure, yes. Then for this ergodic measure, I can find a homological vector such that every point rotates at this speed. So it means that given an ergodic measure, from the point of view of this ergodic measure, everyone goes at the same speed and in the same direction, in the same homological direction. Okay. Another question?
Oh, C is the C, right? That's C.
Yes. Okay. So for instance, one example of ergodic measure is if P is a periodic point of F, say F of Q of P is P, then you have some ergodic measure, which is just the average of the Dirac masses along the orbit. Oh, 1 over P.
Q?
Ah, Q, thank you, yes. 1 point over there. Thank you. Okay, 1 over Q times this sum is an ergodic measure. Oh, yeah, maybe. Okay, suppose it's ergodic. Okay, then R of mu. Okay, suppose. If Q is prime, it will be ergodic, for instance. Then R of mu is just the class of your path. The path when you follow your isotopy until the time 2, Q. Yes?
So for this lemma about F ergodic measure, you don't need it to be non-atomic or anything?
No. No. This is the case where it's atomic. No. I will really look at any F ergodic measure in a moment, because I will look at what is called the ergodic rotation set. Okay, I will define it now, which is the set of all R of mu for any mu F invariant.
Just out of curiosity, is there always a non-atomic ergodic measure for a map F? Or no?
No, because you can have dynamics. Like if you have a north-south dynamics, then you'll have none. But you always have existence of ergodic measures, on the contrary. Okay, so now I will denote by mr of f the set of measures, proba measures. Okay, I should have said this also. Mu is a proba measure. Mu proba, F invariant, and what I will call the ergodic rotation set ergodic. Thank you. Yes, ergodic. So the ergodic rotation set is just the set of R of mu, where mu is an ergodic F invariant measure. And I will denote this set by rho erg of F. And this set is just a subset of H1. Okay, it's not difficult to prove, for instance, that it is a compact subset. It has a lot more properties, but which are more involved. Okay. Now, okay, there is one other challenge, is not to get lost in the blackboards, because I will move on to the statement now. Because all those properties are equivalent to a third one involving this ergodic rotation set. And this property is just saying that the interior of the ergodic rotation set of F is non-empty. Okay. So here also there is one implication which is not so difficult given what's already known, and another one which is more involved and which is most of the work in our proof. So I will first deal with the easy implication, which is 2 implies 3. 3 implies 2. Okay, we have already proved 2 implies 1. Now I will talk about 3 implies 2, and I will finish, if I have time, with some words about the last implication. So 3 implies 2. To prove it, we use a theorem by Gabriel Lelouch. Okay, I don't remember the date, but it's really recent. Okay. Okay, maybe, I don't know. Which is the following. So this theorem uses the intersection form. So if you have 2 homology class, you can associate to them a number, a real number. So if your classes are represented by simple closed curves, this number is just the algebraic intersection number. And then you extend it linearly, and you have a definition of this. So the theorem is like that. You take 2 elements of your ergodic rotation set, and you suppose that their intersection is non-zero. Then this theorem will give you a lot of periodic orbits. Namely, okay, for any epsilon and for any vector in the convex hull of 0, alpha, and beta, there exists a vector Q which is in the intersection of the ball of center R and radius epsilon, such that Q belongs to the ergodic rotation set, and Q is realized by a periodic orbit. Okay, basically, what you have to remember from this statement is that if you have lots of ergodic rotations vectors, along with it, you have a lot of periodic orbits which are turning in a lot of directions. So this implies that if the interior of rho erg of F is not empty, then there are lots of periodic orbits. And then to prove 2, what you do is that you take as a set F a union of sufficiently many periodic orbits. Sufficiently many periodic orbits means that if you look at, say, geodesic representatives of the loops of your periodic orbits, it must cut down the surface into disks. So you cut down completely the topology of the surface with these loops. Then it is not possible, as those periodic orbits are turning in every direction. It's not possible for F to preserve, or any of its power to preserve the isotopic class of a curve. And so F has to be isotopic to a pseudo-Anosov relative to this subset. Cannot preserve restricted to S minus F, any isotopic class of curves of S minus F. So F has to be isotopic to a pseudo-Anosov, I use the classification, the part of the classification I gave at the beginning. Okay, so that proves 3 implies 2. And so it remains to prove only one implication, which is 1 implies 3, and I will just say some word about it to finish this talk. Okay. Okay. So to prove 1 implies 3. We prove actually that if the ergodic rotation set of F has empty interior, then F is not hyperbolic. In the sense that it does not act hyperbolically on the fine curve graph. And to do that, I think I will talk only about one case. So I will say easy case. It is a case where rho erg of F is contained in a rational hyperplane. I mean, a plane with which has equations with only integral coefficients. In this case, you can prove that it's standard.
Is this convex? Is this a convex set?
Not always.
Okay.
Yes, that's kind of the problem. Okay, maybe. Okay, I will explain you why, but at the question stage, otherwise I won't make any explanation here. Okay, so in this case, the idea is that what you do is you look at the cyclic covering associated to alpha, but no, what I mean is you cut along alpha and it makes some covering map. Okay, and you can define a quantity which is just the number of translates which are met by one translate of beta. And this has a nice property. The property, not that difficult to prove, is that it's bigger than the distance between those two curves. So here you take beta isotopic to alpha. Okay? And the fact, this hypothesis that rho erg of alpha is inside this hyperplane, the hypothesis implies, so you have to understand what it means, but basically it implies that this quantity is sublinear. So this implies F is not hyperbolic. Okay, there are other cases to look at, namely if rho erg of F is inside an irrational hyperplane, you use this case, but you make it more quantitative, and you approximate your irrational hyperplane by rational hyperplanes. But there is a glass case, and it will answer your question, where you're not convex. There is a last case to take care of, that you may have a homeomorphism of a genus 2 surface with this curve as invariant curve, but really complicated dynamics here and here. And in this case, in the H1, you will contain open sets in two planes, which are supplementary. So, Okay, suppose you have some orbits rotating like this and some orbit rotating like this, and also here. Then your ergodic rotation set will have empty interior, but will be contained in the union of two planes. And there, we can see somehow in the rotation set that you cannot cross in this curve in the middle. And we use kind of the same ideas as in this case. Okay, thank you for your attention.
Are there other questions?
So does the rotation set depend on the choices that you made? The G, X, Y? How does it?
A good question. So it doesn't depend on the GXI precisely because the GXI are uniformly bounded. And as you divide by n, this quantity will vanish. And also it does not depend on the isotopy, but this is related to a result by Hamström, which tells you that this homeo 0 of S is a contractible space. So two isotopies are isotopic to each other. And this is the reason why they are isotopic, so this is the same homology class that you will get, of course.
Could you give an example or describe the ergodic rotation set for like some particular homeomorphism, so maybe like a point push?
Yes, but the idea, yes. I mean, here you take anything that has a periodic orbit rotating like this here, and a periodic orbit rotating like this, then it must have something complicated behavior here. You make the same thing here, and you will get actually the union of two convex subsets contained in two different hyperplanes. One contained in R2 cross 0, and the other one contained in 0 cross R2.
And in that case, is that all of the ergodic rotation set?
Computing it precisely is more difficult, of course. So we know, okay, because here I'm a bit sloppy, we know you have at least those two rotation vectors, and also we know that on each of those planes which represent these two subsurfaces, this will be a convex subset. So it will be convex. You know it contains some vector representing this, some vector representing this, and the same here. And then if you are careful, it shouldn't be a lot bigger than the convex hull of those homological vectors.
Any other question?
Is there anything canonical in F? That is, certainly you can try to make F the set the smallest possible. Is there, for example,
I'm not sure it's
two realization with a minimum. Are
there? I don't know, but I guess you can choose very different isotopy classes when you take your subset F. So you can take very different periodic orbits, which will make this thing work. So I would guess it should be difficult to prove that even if you take the minimal number of points, it should be conjugated.
Thank you very much. Are there other questions before the break?
tomorrow, and there will be examples. It's easier somehow.
Yes.
He said he will deal with the Torres case tomorrow, and there will be examples. Thank you very much.